So before I get into the lectures on efficiency, are there any questions? Just some general questions. I realized last lecture was it's difficult to follow. Well, I think it is when I rewatched it. That's a lecture that's just supposed to spark some thoughts that are supposed to carry over for many weeks. This on efficiency is a topic that if you don't understand everything on these slides or these lecture notes, you should review them, because this is the most practical stuff that you'll be applying. Okay, so philosophical, conceptual, what's going to help you, invent new things, be innovative. That's kind of some of the other lecture material. This is what you'll be expected to understand, to be practical, right, in the engineering workforce. So, efficiency, I said this before, describes how well an energy conversion or energy transfer process is working relative to 100% efficiency. So efficiency is true, right, for that, relative to 100% transfer or conversion. Now, I mentioned that there's two main efficiencies: the first law of efficiency and the second law of efficiency. And then if you go based off the textbook, you're not going to read about the second law of efficiency until chapter 8. And that's why I'm introducing it now in basically chapter 2, because it's equally, if not more important than the first law of efficiency. It's just more complicated, and it deals with the second law. First one also deals with the second law, but not directly. And this first law of efficiency here, if you look up here, it says relative to 100% transfer or conversion. The first law of efficiency, actually, it's relative to 100% possible transfer or conversion. So the first law takes into account, well, yeah, if I wanted to convert all the energy, then it would be 100%. But no, the first law is going to say only 80% is really what we're going to consider that can be converted. And then out of that 80% of all of the energy, I'll use an efficiency calculation. So it's kind of like 100% of 80%. So the first law kind of does a little, which is fine in some respects, but it does a little bit of, you could say cheating, right? It says, okay, there's 10 kilojoules of energy, but we're going to say only 8 kilojoules of that, 8 kilojoules of the 10 kilojoules of total energy can be converted to what we want. The other 2 kilojoules, we're just going to say that it still can be used somewhere else, but we're not going to try to use it for our process. Second law of efficiency says, hey, you can't skip out on those other 2 kilojoules of energy. You need to take that into account. And so hopefully we can see this in the next few equations and descriptions. And so a first law, second law, and I can use the subscripts, and sometimes they're the same, but usually not. And so then I have this equation, first law of efficiency. So I'll just go over the first law of efficiency. And so I can say A to 1 is equal to the energy out useful over the energy in spent. Okay, so that's kind of a standard way of looking at it. In the book, what they put is energy out and then energy in, and they don't really say useful or spent. And then for different situations, they replace these with what is actually energy out useful and what is actually energy in spent. And I'll get to a couple examples with the turbine and pump of that. Another way to write it is 1 minus energy loss over the energy in spent. And then this loss energy is usually heat, and it's not just heat, but the irreversible heat. The heat you can't do anything with. So if there's a bunch of heat coming off a volcano, right? We can use most of that. But there's a portion of that heat coming off the volcano that we can't really do much with. And that's the irreversible stuff, or the unuseful heat. So this energy in spent, this is the energy used to perform a particular task, right? So this is when I was talking about if there's 10 kilojoules of energy, total energy, and then if we say 8 kilojoules of that is is what we're going to do something with. So that would be the energy in spent. It would be the 8 kilojoules of the 10 kilojoules total. But this is the energy in spent. So the energy that went into our system to serve a purpose. So I guess I can draw a little box here. And so I can have some energy in, right? I thought I had one of these, but I guess so I have some energy in, and then related to that, I can get some energy out, right? And I can get some work out. And then I can get some Q loss. So I have energy in, the total amount of energy into my system. And of course I should draw, I'll just put a boundary there. So I have this energy into my system, and then I get some energy out, and then I get work out. So this is actually, this one here, the workout. So let's just say we have a device that's gonna do work. We're gonna put energy in, and then it's gonna serve a purpose. It's gonna have some work output, okay? So we could say that this is some type of energy producing device, whether it's an engine or a turbine system or whatever it might be, a generator or something like this. So this workout is the energy out useful. So this is what we wanted, okay? Whether it's electric power out, whatever it might be, right? This is what we wanted. Whether it's shaft, torque, power out of the engine, whatever it might be. So useful energy out. Then we have the energy in. So this is all the forms of energy in. And then we have some energy out here, and this one is the energy still usable. So I'll just put SU for still usable. So this is the energy that we can still use, but not for the particular task at hand. I'll just put some dots at it. So this energy we can still do something with. So let's just say that this is something else, say a fluid pump, which I'll get to in a second. But I have some fluid in, and then I have fluid out, and then I have the main fluid. Oh, let's not. I don't know. But this let's forget about the fluid pump. We'll use a better example in a second. This energy we can still do something with. So I could put another subsystem here. Okay. And I could have another system 2, and this energy out, still usable, can go into here and be converted to another form of energy. Okay? So this is still usable. So I could have, so if this is my car, and then this is my cell phone, I could use some of that energy from my car that I'm not used to driving it, right? And I could use it to do something to my cell phone or something, whatever it might be. This stuff here could actually be used to be converted into some type of work. Now this energy out loss, this Q loss, so this is my energy out, and I'll put NU for not useful. If I were to put a box up here for another system, there's no way I could use any of this to do anything. There's no way I could have that as an energy input for conversion. It's lost. There's no way, I can't. It's like in the ether of the universe, or however you want to describe it. It's lost. Or maybe it's not completely lost. We don't have any means or any technology to date to do anything useful with that. Okay? We don't know how to make it useful. Because it is energy, so in principle you could convert it, but we don't know how to make it useful. So we consider it irreversible heat, or it's lost energy. So energy out useful, energy successfully transferred. I said this in words. Or converted for the particular task at hand. And then the energy loss, it's energy out that we weren't able to do anything useful with. And I'll just do an example. For example, irreversible heat. Okay. So this is our system it's going to convert energy to one form to another. So it converts a bunch of the energy input to some work output, and that's my energy out useful. Of that energy in, not all of it is converted to work, and then some of it is left over that we can still do something with, but then there's a portion that isn't converted that we don't know how to do anything with, and we could say it's completely, we don't know anything how to convert it, and it would be irreversible heat. So by definition, we don't know, it's irreversible. Okay? Or it could be some other form of energy, right, other than heat, that we just don't have a technology or not intelligent enough to convert in some way. It's the loss energy. And so I can write all these in that expression, and here's just some descriptions. Now I've never seen anywhere that describes it like this. Okay, so this is after teaching the class many times and then having somebody else mention, isn't a better way to describe this energy is energy unspent? And I was like, yeah, and he goes, oh, my high school physics teachers described it that way. But, so in a lot of textbooks I don't see it written this way or described in that form, especially in our textbook. But I think this is the best way to think of the first law today. So let's do an example. So we'll do a pump, okay? So for a pump, what do we have? We have some energy in, and then there's going to be fluid flow in, right? And then we have some energy out, fluid flow, okay? But in a pump is an energy consuming device, so we put energy in, it consumes energy to perform a purpose. So a turbine, or some are energy producing devices, some are energy consuming devices. Pumps are energy consuming devices. So you have to make the distinction between an energy consuming device or energy producing device. So we have some energy in, right? We have some energy in fluid flow, plus we had some energy in shaft. And this energy in shaft was just work in shaft. Right? We make the pump turn around, and we increase the pressure inside, and we introduce a pressure difference, so we can get higher flow or higher pressure flow, right? And then so we have these two forms of energy in, and we get energy out. So the really useful, or the stuff we really want, what we're trying to do, the pump is serving a purpose. We want to bring the water from sea level up to a water tower, so we have to overcome gravity, right? So we have to increase the pressure of the fluid to overcome that gravity. Or we want to increase the velocity of the flow, so we put in energy to increase the velocity of the flow. And so we do that, and we put in some shaft work to do that, but it's not a 100% efficient process, and there's friction with inside, so we end up generating some heat, right? And there's a portion of this heat that we don't know how to do anything with, and so we can consider that as the energy loss. So if I'm going to use this equation above, I can plug things in. And so my efficiency, first law efficiency of the pump, and this up here should be energy out useful. Okay? Well, the energy out useful is actually energy out fluid flow minus energy in fluid flow. And then this was in the denominator was my energy in spent, but my energy in spent is just basically work shaft in shaft. Okay. And then I could do it this way, 1 minus, this one's a little bit easier, so that this just ends up being Q loss, heat, over work in shaft. So you can see the 1 minus is simpler to kind of just based off drawing this picture to get to the first law efficiency. Now, conceptually, why is the energy out useful, this out minus in? Because if you think there's so remember when I said there's 10 kilojoules of energy coming in? So I could say that this was 8 and this was 2, and if I add this plus this, it ends up being 10. Now, what we're doing is we're putting energy in, and so this came in with, say, 2 kilojoules of energy, okay? And what we need to do is we need to increase the pressure inside, or the velocity, so we have to increase its kinetic or potential energy. So we need to take this from 2 to say as much as possible. But it doesn't come in at 0. It's impossible to bring fluid into my pump at 0. So this is always going to be the extra boost to it. So that's why the energy out useful is actually what we increased from the fluid prior. If we were to be able to take in energy into the pump from absolute 0, right, temperature, so we take in a fluid that was at absolute 0, right, temperature, 0 Kelvin, and had no kinetic energy, then this energy in would be 0, and then we wouldn't have to worry about this energy in. But the reality is, it's impossible to put fluid into a pump with no energy. So in this case, we're always going to get some nice efficiency, but the second law would take into account the fact that, hey, you're kind of cheating the system, because you could do certain things with this energy and fluid flow. So really, there's an extra efficiency. It's not as efficient as you're saying. And so just an equation for an energy in spent equals work shaft in, and then energy out useful equals energy out fluid flow minus energy in fluid flow. And so I can rewrite that energy in equals work. I said all this stuff in words earlier. Work shaft in plus energy in fluid flow, and energy out is equal to Q loss heat plus energy out fluid flow. And the energy out fluid flow. What is the purpose of the pump? To increase the energy of the flowing fluid out, right? That's the purpose of a pump. It's to move liquid from, to increase its kinetic energy or potential energy, so we can overcome a potential barrier, right? To bring a control volume of liquid from here to 1,000 meters above my head requires energy, because I have to work against gravity. So I have to increase the energy of that control volume in order to overcome that. And so you just use a bunch of control volumes connected to each other, and the bottom one has the highest pressure, and then it overcomes that. But right at the outlet of my pump, I need to have a high pressure to overcome that column of water above it, or the energy required to bring. I could calculate the energy for a monkey walk up a ladder, all the way to the top of the tower, right? And so you could have, I don't know, but you get the general idea. You have to overcome some energy. So the pump does that. Okay, so second law, first law of efficiency. Let's do another example. So the last one was of a energy consuming device. So now let's do of an energy producing device, a turbine. So this is a standard kind of like pictorial view of a turbine. So in this case, I have some energy in fluid flow, and then I have some energy out fluid flow, and then I have my energy out useful, which is the work shaft out. Okay? And of course I have some heat loss. There's always friction or something going on inside. Things heat up when they operate, so you end up getting some irreversible heat or some. And so I'm lumping in a lot of this energy out that is not useful into, I'm just saying it's heat. But there could be more forms. So first law efficiency, so again I have that same form, that is the energy out useful over the energy in spent. So my energy in spent turns out to be energy in fluid flow minus energy out fluid flow. My work out useful is work shaft out. And I can write it in the 1 minus form. And so then I just still have my Q loss, and then it's energy in fluid flow minus energy out fluid flow. So, if you're going to have a turbine system, and you could have something that heats up a fluid, And so a lot of times in these turbines, you have a steam coming in here, a superheated steam. So you can just have water vapor at, 2000 C, 4000 C, right? Hot, high energy water vapor. And then that turns a turbine, and then the output is a low energy steam. But the reality is when you do this, you have some high energy fluid coming in, which turns the shaft and whatnot. You don't output fluid at 0 Kelvin, zero velocity. You don't output a fluid that's static and is at absolute 0 temperature. So there's always going to be some internal energy associated with and kinetic energy associated with that fluid out. So you never really converted. Now this stuff is still useful. So this is my energy out and then still usable, right? I could still do something with it. So, just by inspection, right? Another way to do this. If I said that there was no irreversible heat generated in this turbine, the first law of efficiency, this Q loss would be 0, right? Which means that the turbine would be 100% efficient. But I still have some energy out. I didn't convert all the energy. That's where I'm getting, we're going to say, well, really we're only going to say that, 80% of that energy input we're going to do something with, and we're going to say our efficiency relative to that. Because we know we have to have, if this is 10 kilojoules coming in, we're going to say that, 2 kilojoules, we're never really, we can't really decrease the energy of the fluid out to 0 kilojoules, because we have to have fluid out. So we're just going to say that of the 10, 8 we're going to use as an efficiency. And that's why we divide. If this is 10 and this is 2, we divide by 8. So the first law of efficiency kind of cheats. And you can see that a little bit better when you look at a turbine, an energy producing device. Energy consuming wasn't quite as clear, but I think with energy producing it's much clearer. So you can see that this is good, it's useful, right? You can get a realistic amount of kinetic energy and potential energy out. You might want your fluid to come out at room temperature and only flowing at a few, the perfect velocity to move it to the whatever lake or something like this. So the second law of efficiency, this one deals with both reversible and irreversible. So this one takes into account, the one doesn't cheat and say, we're gonna make my own little restriction on what is the amount of energy that I'm going to say needs to be converted. This one takes into account for all of it, and so reversible, your work done, and it can be either work done on or by, and we were dealing with on or by earlier. We just said energy consuming or energy producing devices. And so for the second law of efficiency, I'm going to write down a bunch of equations. Really, you're not going to apply these until after, for like a month from now. But I'm introducing the idea of the second law of efficiency. So if I ask you, if the Q loss in this process went to 0, would the true efficiency be 100%? You'd be able to say no, but the first law of efficiency would say yes. So if I were to ask you a test question, I'd have you solve for the first law of efficiency of a turbine, and you would, and then I would say, is the true efficient if Q loss, if you could make the system and Q loss go to 0, would the true efficiency be 100? And you'd have this equation that you derived in front of you, and it would say yes, but that's the first law of efficiency, not the true efficiency. So you can answer questions like that. Be able to make the distinction between the true efficiency and the first law of efficiency. Okay, so second law of efficiency, energy producing devices and energy consuming devices. And so for an energy producing device, like a turbine, it turns out to be work out useful over work reversible. Okay? And then this is the useful work output. And this is the maximum possible work output. So we talked about reversible but irreversible process. So if my turbine or my energy producing device was a reversible thing, then I could say that there's some reverse, I would have no area, Q loss, right, in a cycle, in those curves. So all of the energy would be converted to work. I wouldn't have any losses. And so then the work output would be 100% reversible. Now the reality is we don't have things that are, a reversible process is a figment, right, of our imagination, or a concept we need to do to define irreversible, right? A more realistic, practical example of what happens in day-to-day life. But, by defining something that's reversible, we can get relative to the maximum possible. So maximum possible work output. There is no irreversible heat output. Okay. Now for energy consuming device, it kind of switches around. This would be a pump. Then it ends up being work reversible, but this is the work reversible input over work useful. So this is the minimum possible work input, and this is the useful work input. So for the pump, we had this expression where we had the energy in fluid flow, or the energy, the energy in spent, right? This was, for the earlier case, we had the energy, when we did the first law of efficiency, it was the energy in spent. And so this work useful input, right? And then for the pump, we had a shaft input. And so we had some fluid flow in, plus we had shaft into the pump. Well, the work useful input is just the shaft, basically the shaft input here. So it's very similar to before. But we have these two forms, and you can see they just get flipped, and then there's ones, this is output and this is input. And so for both, I can say the work useful is the work actual minus the work surroundings. Now the work surroundings, this has to deal with if I blow up a balloon, and I make the balloon bigger and bigger and bigger. What am I doing? I'm displacing the air in the surroundings. So I'm doing work on the surroundings. So in some cases, you might have devices where I'm displacing or they're expanding. And so this work surroundings, you can kind of think of it as the PV of the surroundings. PV work of the surroundings. And then the actual work for this pump, this is the work shaft in for the pump. Okay? And then work useful for this turbine, this is this work actual. Since these devices are not displacing air around them, I guess they do, they might thermally expand when they're running. But let's say that they expand very little. So this work actual for the pump, right, is going to be work shaft in, and then for the turbine, it's going to be work shaft out. So the worst, and then for these two cases, we could say that this went to zero, the work surroundings. So the work useful in is that, and the work useful out is that, and then I have to calculate the work reversible. Now the work reversible kind of gets a little, so now the work reversible is equivalent to the work useful, and then I have to put a minus sign, and then there's this plus/minus T0 S gen, and then the plus sign, I use the plus sign above for turbine, is for a turbine or energy consuming device, and the minus sign corresponds to a pump or energy consuming device. Okay? And Another way to write this is, I guess I could say work reversible, and then I could say plus minus T naught S gen. Okay. Now, so this is the entropy generated, and this is where you do calculations, and you calculate, so we haven't got on how we calculate the entropy generated yet. We've only talked about the concept of entropy. And so later in chapters 7 and 8 and 9 and whatnot, we're going to deal with how we actually calculate the entropy generated. So you'll solve a problem to calculate the entropy generated, and then from that you can calculate the second law of efficiency. So I'm just introducing the idea that you use entropy, and then there's such thing as the entropy generated. And so for I'm just going to ask the question, for a reversible process, what do you think the entropy generated is? Zero? It is. For reversible process, the entropy generated is 0, and you can see that right here. When entropy generated is 0, work reversible equals work useful. Okay, so it doesn't matter whether I have an energy consuming or energy producing device. Both of these. So if I develop a reversible pump, right, or a reversible turbine, the second law of efficiency will be 1. Of course, we're never going to do that because we're going to. I don't know. Maybe you. I don't know. I doubt it. Right? You're not gonna. I shouldn't say you'll never do it. Thermodynamics says it can be done if you create a reversible process. Okay, you're not violating any laws. So usually we have irreversible processes when we operate them and then try to operate them in the opposite direction. There's always going to be some area under the curve, or if we just go through a cycle, there's always going to be some irreversible heat loss. And in that case, there's going to be some entropy generated because we have those irreversibilities during the process. And then we calculate those, and we can take into account the useful work relative to the maximum amount of reversible work. So, entropy generated. Okay, so we'll focus on this after chapter 7, but now you know that there's a second law of efficiency instead of the first law of efficiency. So there's some other efficiencies, and they're not really other efficiencies, but I guess they are other efficiencies, but they all kind of come back to their efficiencies. And so there's a thermal efficiency, and an example is a heat engine. And so I can write the thermal efficiency. So this one kind of is similar to the first law efficiency. If we do it like this, so we have some Q in, right, and we can get some work out, and then we can get some Q out. And so for a thermal, and this would be a heat engine, and then by doing that, what is it? Energy out, useful is my work out, and my energy in spent. And if I were to say that all of this was converted, right, it's my Q in net. Okay? And then I can write it in another way. 1 minus Q out loss over Q in. And so associated with this heat in, if I draw my system, that's a heat engine going through a cycle, which that represents a cycle. I have some heat coming in, but we can't define heat of a vacuum, right? We need some vibrational modes. So there has to be a mass associated with the heat carrier. I guess you can have radiation, but still the radiation is kind of something between a source and a receiver. You need mass over here, you need your source before you feel the heat from the radiation. So in principle, if you only had a sun in the universe, you wouldn't be able to define heat because there would be no receiver, I guess. But nevertheless, okay. So we have some mass, right? And so this mass is going to come in, and then there's going to be a temperature associated with this, right? Tn. and then we're going to have some heat output, but we'd like to say that there's a temperature associated with that heat output. We can correlate these two. And it's easy to correlate these two if we use mass, and I could just write down a simple equation, right? Q equals mCp delta T. So I can relate the heat associated with a mass at a given temperature using the heat capacity of the material. Anyways. So this one here, so I have the thermal efficiency, and the Carnot efficiency is kind of an extension of this, where it deals with a reversible process, or a reversible heat engine, and then I can say T out over T in. So instead of this Q out loss, then I just have T out, and then T in is that. Okay? I write it as such. And then, for a heat engine, how can that work? Well, I can make an example. I could have a volcano. Okay? And then from the volcano, I have some heat that's coming out at high temperature, right? I have a high temperature output. And then I got that, and then this heat engine has to reject this, and then I reject it into the ocean. Okay? So then I got some heat coming in and low T, right? So I have some engine that works, and I take the heat, high energy heat from a volcano, and then I do some work with that, and then I reject the remaining stuff to the ocean. And later on we'll talk about how you need both a source and a sink in order to have, a heat engine. I can't just have a volcano, a system, and work output. I actually have to reject. You always have some heat you have to reject. But we'll get to that. But here's just an example of a heat engine. Now, I'll just make one comment related to this. So it's not always just a heat engine. You could have something else, right? You could have a power plant offshore, or let's do a desalination plant. Okay, we have a desalination plant offshore. Well, the desalination plant is cleaning water, okay? And when it's cleaning the water, it's not 100% efficient, right? The process is only so efficient. Well, it's going to generate a lot of heat, and it has to reject that somewhere. Otherwise, the plant's just going to increase in temperature, right? Or the processes within. So it rejects. Usually you see these desalination plants or maybe power plants next to large water sources. And so what they're doing is they're rejecting a lot of that heat to the ocean shoreline. So one of the big challenges for environment is finding a way to create better, more efficient systems or processes for large industrial systems. So we're not killing the ecosystem of the shoreline habitat. We're rejecting too much heat to our shorelines, and we're killing, coral reefs and things like that. And that's like one of the top things in terms of environmental DOE. It's a current major problem. You don't hear a lot about it, but anyways, just a side note. Okay, so Carnot efficiency, we can do that. And so here's just an example of my energy in. I can write it as, KB T in, and my energy out, KB T out, right? Temperature, joules per Kelvin, joules per Kelvin. Get energy out, energy in, heat out. And so let's do an example of how we can use the Carnot efficiency to determine the efficiency of something. So let's do of a diesel engine. So I can say 1 minus, and then it's going to reject. So my diesel engine rejects all the fumes and things like this to the temperature of the surroundings. Thank you. So let's do this. So I just wrote these equations up earlier. So let's do an example of the diesel engine with Carnot efficiency. And so 1 minus, now this should be T out, and so if I have a diesel engine, it outputs, we're going to say it outputs to the surroundings, which is at, my car operates, if I'm in Alaska right now, the surroundings is minus 30, right? If you're in Florida, it's quite nice relative to Alaska. But anyways, you get that, and we have you could have a truck, Ford F-150 in both Florida, and the surroundings would be different based off that, but it's still an engine. So and then it operates at a given temperature, and so this would be the temperature inside engine. Okay. And just to put in some numbers, we'll use Florida, or maybe not Florida, room temperature. It's not quite room temperature outside, but it's close. And we'll say that inside my diesel engine, it's operating, the combustion and all that stuff is happening at 600 C. Might be a little bit low, but I just chose these numbers because it's easy to. This is right. I just want to do easy math. So I can divide by 2 easily. So I have 300 over 600. Well, if I have a gasoline engine, it actually turns out the gasoline engine operates at a slightly lower temperature. So gasolines operate at slightly lower temperatures, to say 550. So you can see that a diesel engine is always going to be less efficient than a gasoline engine based off of this Carnot efficiency because of a lower working temperature. And you can see that if I take my engine and I run it, based off purely Carnot efficiency, it should be more efficient in a cold environment than a hot environment. Yes?
So it works with Celsius, or do you have to do...
It has to be Kelvin, but yeah, so that's why I put C, but... Right. I put C, but it wasn't C. I put 300 for a reason, for room temperature. Okay, sorry, but thank you for bringing that up. It's K. 300 K room temperature and 600 K. 300 Celsius, or 2 something. But anyways, so we have that in 50%. And then but you have glow plugs, and so if you operate it at a different environment, so colder environment might mean more friction, so you have more losses. So, but this Carnot efficiency doesn't take, it has nothing to do with any friction or losses or irreversible heat. It's just looking at the temperature of the input of the source in the sink. And it's saying based off of the temperature of my volcano and the temperature of my ocean, I can calculate the maximum possible efficiency of that engine. And likewise, for my diesel engine, based off the temperature you say it's going to do all the combustion at and the temperature of the surroundings, I can calculate the maximum efficiency of that process. And so I could do that. I could compare a diesel engine to a gasoline engine, and just by based off that and knowing the temperatures, you can calculate the maximum possible efficiency of each. And from that, you can say, yeah, I'm better off having something that operates at a higher temperature. But with the fact that you want to make something that operates at a higher temperature, it might give you a higher Carnot efficiency, but that means materials that are high temperature might be more expensive, right? So there's other complications of engineering with making things run at higher temperature. And just look at it as put the oven at 200 Fahrenheit versus 400 Fahrenheit, and keep your hand in there a little bit. With a glove, you're gonna need a better mitt, right? You're going to need a better engineered mitt to keep your hand in there, at different temperatures. And the same with material properties. Copper melts at, things corrode, right? You take a piece of aluminum, you put water on it, and you boil on it, it starts to corrode. So there's always some water and stuff in gasolines. You never get rid of all of it. Okay. So we have this, and then I have another example. So QN, or TN, and Q out, T out, and work out. And total efficiency, so eta total, so that deals with systems. Total efficiency. So there's the product symbol, if you remember from Calc 2, use the product symbol. So there's a summation in the product, and then so I have eta I. So if I have a system with subsystems, I could have a system consisting of lights, pump, motor, and turbine. And each subsystem has its own efficiency, but the whole system ends up being the product of all components. And so the total efficiency of a system is going to be eta motor times eta pump times dot dot dot. And so just as an example, I could say the pump in this system has an efficiency of 40%, the turbine 50%, the motor 60%, the lights 80%. And so I go through all of that and I do the total efficiency and it ends up being 10%. So if you're an engineer and you do this, where would you want to, where would you focus your time on increasing the efficiency of the system? Pump or turbine, right? The lowest efficiency, the lowest link. That pretty much sums up, the lectures on efficiencies. But now you know there's a difference between the first law and the second law. And you can always use the Carnot efficiency, or if you know two temperatures, to kind of give you an upper bound. So I always recommend that you do simple calculations to kind of give you an idea, and then you can go to more complicated calculations.